In the early 1980s, automation was split down the middle. On one side, computer science, glowing terminals processing logic. On the other, mechanical engineering, heavy robotic arms executing rigid motions. The two had to merge. Thinking and moving operated in completely isolated silos. The algorithms didn't have bodies, and the machines didn't have brains. The U.S. Army recognized this bottleneck. In May 1982, they tasked SRI International with finding a way to bridge that gap. This document is the result of that mandate, the R&D Plan for Army Applications of AI and Robotics. SRI was asked to build a comprehensive development plan for autonomous combat systems. The problem was they had to do this decades before the microprocessors, sensors, or algorithms actually existed to make those systems a reality. To solve a hardware problem with hardware that hadn't been invented yet, SRI engineers had to start with pure theory. They needed to draft an architecture that unified the digital brain and the mechanical body into a single closed-loop system. This diagram is the core of their solution. It's SRI's unified model, mapping the theoretical relationship between artificial intelligence and robotics. They designed the system top-down, starting with an absolute prerequisite for any machine operating on its own, an internal representation of reality. The world model is a persistent digital state store. It holds the machine's representation of the battlefield, tracking spatial data and tactical conditions. But an internal map is useless without a cognitive engine to update it. That sits right below it, in the reasoning node. Reasoning is the decision-making core. It evaluates the current state of the environment against a set of programmed goals and consults expert systems to determine what the robot should do next. You can see exactly how SRI categorized the demands on this cognitive engine by looking at the report's structure. The reasoning node is responsible for assimilating incoming information, consulting expert databases, generating action plans, and constantly monitoring ongoing situations to ensure those plans are working. This creates a perfect isolated digital mind. To interact with the messy physical world, the system requires a layer of translation. SRI needed a software interface to act as a translator, sitting directly between the raw hardware and the reasoning engine. That brings us back to the diagram, specifically the middle layer labeled Interpreting and Generating. Interpreting acts as the inbound translator. It takes raw, unstructured signals from the sensors and converts them into symbolic variables the reasoning engine can actually compute. The computational load required to pull this off is massive. Before the reasoning node can make a single decision, the interpreting software has to process computational vision to recognize shapes and parse natural language to understand human commands. Generating handles the exact opposite problem. It is the outbound mechanism that takes the abstract plans created by the reasoning engine and compiles them into concrete commands. Whether the robot needs to drive across a field or pick up an object, the generating node breaks that intent down into distinct, executable instructions for mobility and manipulation. The SRI engineers knew this translation step was highly theoretical, dedicating entire sections of the report to the unresolved research issues involved in making these conversions reliable. This software interface is the ultimate bottleneck of autonomy. It is the mandatory checkpoint where physics becomes data, and data turns back into motion. Below the software lies the final layer of the architecture, the physical envelope of the machine itself. Sensing represents the raw hardware arrays that gather data from the environment and push it up into the interpreting node. The report outlines an extensive requirement for sensory hardware, far beyond simple cameras. To navigate a chaotic physical environment, a machine relies heavily on tactile feedback and range sensors to map immediate obstacles in real time. And on the output side, effectors are the physical actuators, hydraulics, and motors that carry out the movements. This categorizes every piece of moving hardware on the platform, broken down strictly into hands, arms, and legs. In the early 1980s, this meant heavy, specialized industrial equipment, like this rigid mechanical arm, designed for very specific, repeated actions. By attaching this final hardware layer to the digital mind, SRI completed their map. They had drafted a fully integrated, closed-loop architecture for autonomous operation. To prove this architecture worked, SRI used it as a diagnostic tool. They ran theoretical Army systems through the model to identify exactly where 1980s technology would fail. One of the prime candidates they analyzed was an automated mine clearer. If we run a mind clearer through the unified model, we can trace the exact path of a single decision in the field. First, the physical sensors roll over a metallic anomaly. That raw data is passed up to the interpreting software, which classifies the signal as a potential landmine. The reasoning engine receives that classification, updates the internal world model with a permanent hazard marker, and plots a course correction to avoid the threat. Finally, the generating node converts that new path into voltage signals and steering commands, passing them down to the effectors to physically turn the vehicle. Breaking the process down into these 5 steps allowed engineers to isolate the technological gaps. They could clearly see the required hardware for locomotion existed, but the software for automated navigation and visual mine recognition was years away from viability. The mine clearer was just a single test case. The true scale of SRI's work becomes apparent when you look at their overall methodology across the entire project. They evaluated 100 separate automation concepts for the military and distilled them down into 10 broad functional categories. From there, they selected one specific example from each category, like the mine clearer or a tank ammunition handler, to find the overlapping technical requirements between them. The ultimate output of this analysis was a highly concentrated, prioritized list of 97 specific research tasks. The report clearly indexes these requirements, establishing an exact roadmap for developing computational vision, action planning, and mobility control. Look at a modern autonomous system today. The code driving it is entirely different, often relying on neural networks and machine learning, rather than the hard-coded expert systems of the 1980s. But the underlying architecture remains exactly the same. The core loop, sensing the environment, interpreting the data, reasoning about a goal, generating a plan, and effecting a physical change, is still the absolute foundation of robotics. SRI's 1982 report outlined a research path that spanned decades. They built the systems engineering model required to actually construct autonomous machines, providing a blueprint that outlasts the hardware of its era. In the early 1980s, the military faced a strict strategic barrier. They wanted to automate warfare, putting machines on the front lines instead of soldiers, but the required computational technology simply did not exist. This is the May 1982 final report produced for the U.S. Army Engineer Topographic Laboratories by SRI International. The report served as a rigorous research and development plan, evaluating technological feasibility across 10 distinct categories of military operations. The scope of the initial study was massive. SRI identified exactly 100 distinct theoretical concepts for autonomous combat and support systems. That volume created an immediate prioritization challenge. Funding 100 disparate concepts, ranging from basic data access tools to fully autonomous fighting sentries, requires a specific logical method of evaluation. The military needed a way to map abstract cognitive tasks, like spotting an enemy target, to physical hardware in order to identify the shared bottlenecks holding development back. To solve this procurement hurdle, SRI developed a universal framework capable of dissecting any future weapon into its fundamental parts. At the time, development was split between 2 isolated disciplines. Computer scientists worked on thinking, the artificial intelligence, while mechanical engineers worked on moving, the robotics. This diagram is the architectural solution SRI proposed to bridge that gap, the unified model of artificial intelligence and robotics. This 1982 framework laid the precise engineering groundwork for how autonomous systems are structured today. It frames the machine as a continuous circular loop of data and physics. By breaking the system down this way, the Army could isolate hardware or software failures on paper long before a physical prototype was ever assembled. Standardizing the architecture meant the military could fund research into individual software and hardware modules, rather than pouring resources into complete, non-functional machines. Analyzing the mechanics of this model reveals how the military formalized the transition from theoretical AI to actionable R&D. Let's break down the architecture step by step. Every autonomous system begins by confronting the physical environment through raw input. That input is captured here at the sensing node, which records raw physical data like light, heat, or pressure from the outside world. That raw data flows upward into the interpreting node, where it is translated into structured computational information the AI can actually process. Now the data reaches the cognitive core of the machine, the world model. The interpreted data feeds into this massive internal map of reality, maintaining an understanding of its surroundings. Inside that world model sits the reasoning node. This is the brain of the system, making tactical decisions based on pre-programmed goals. Once a decision is made, the architecture shifts to the output phase, translating computational thought back into physical reality. The abstract decision flows down into the generating node, which converts the choice into a specific executable action plan. Finally, the plan reaches the affecting node. This is where the system interacts with the physical world, manipulating an object or moving a tread. That physical action creates a change in the environment, which is instantly picked up by the sensors, closing the loop in continuous feedback. By isolating these distinct nodes, SRI gave mechanical engineers and software developers a shared map to build from. With the unified model established, SRI had to filter their 100 initial concepts through this new lens. They abandoned traditional military divisions, like sorting by infantry or artillery, and organized the concepts using a new metric called technological similarity. Technological similarity grouped systems based on their specific bottlenecks. If two machines required advances in the exact same nodes of the unified model, they were grouped together. This filtering process collapsed the 100 sprawling ideas down into 10 foundational categories of military AI and robotics. Some categories are heavily cognitive. Expert advisors and planning aids put almost all their stress on the reasoning node. Compare that to actuation-heavy categories, like handling support systems or weapons, which demand serious advances in the physical affecting nodes. This categorization proved an important point. At the software level, a frontline combat drone and a logistics loader might be the exact same machine. To stress test the framework, SRI mapped two highly specific military applications against the model to expose their hidden technology gaps. The first case study was a tank ammunition handler, classified under handling support systems. The physical constraints are severe. The machine must manipulate heavy rounds inside the cramped interior of an armored tank. When mapped against the unified model, the ammo handler requires almost no complex reasoning. Instead, it demands advances in actuation and physical grip. The second case study was a mine clearer, categorized under support systems. The constraints here are entirely cognitive. It doesn't need complex physical arms, but it must map varied hazards in unpredictable terrain. Mapped against the model, the mine clearer puts virtually all its stress on the input phase, sensing and interpreting radar or ground data. Mapping the 10 categories this way allowed SRI to quantify exactly what technologies were missing across the board in 1982. The final count was 97 specific research topics. The report detailed the exact number of tasks required, identifying 12 discrete tasks for computational vision versus just 4 tasks for manipulators. The unified model turned a sprawling wish list of concepts into a highly precise, itemized invoice for fundamental R&D. With the 97 technology gaps identified, SRI delivered a harsh truth. The military could not build a fully autonomous combat robot. The components simply did not exist. Highly ambitious concepts, like a light fighting sentry, were explicitly deferred until the year 2000 due to these gaps. Instead, the R&D plan forced a strategic pivot, prioritizing systems that could be executed with technology that existed right then. SRI recommended a short list of 4 near-term candidate applications for immediate development. These 4 were chosen because their critical nodes on the unified model did not require major leaps in fundamental computational vision or reasoning. The mine clearer received an immediate, highly focused push, serving as a pragmatic, physical starting point for Army robotics. These early projects were built as rudimentary, evolutionary versions of what they would eventually become. True strategic planning requires the discipline to focus resources entirely on what can be fielded immediately while identifying what must be deferred. The most vital legacy of the 1982 report is the concept of evolutionary modularity. Because the unified model cleanly separated functions, treating interpreting and reasoning as distinct blocks, systems could be built with swappable components. This gave the Army a massive procurement advantage. They could field a basic system in 1985 and simply wait for computer science to catch up. A system is upgraded over time without rebuilding the physical machine, simply by swapping out obsolete software nodes. Advances in natural language processing or vision algorithms discovered a decade later could be plugged directly into existing tanks or planning aids. This strict separation of hardware and software modularity is exactly how modern defense contractors and tech giants engineer autonomous systems today.
The SRI team possessed the foresight needed to map out a rigid architecture for technologies that barely existed. The 1982 R&D plan drafted the exact blueprints that defense agencies eventually used to build the future of military robotics.
To understand the modern military robotics pipeline, we have to rewind to the era of early 1980s computing. This document is the May 1982 final report commissioned by the U.S. Army and executed by SRI International. The Army's objective was to map out the future of artificial intelligence and robotics across combat and combat support operations. Note that this document was publicly released. We are looking at a real, unclassified engineering assessment. The Army faced a distinct problem. They did not need a science fiction wish list. They required a realistic, engineering-based timeline. The challenge lay in calculating what was mathematically and physically possible to build, using the existing constraints of 1980s technology. To calculate that, SRI had to engineer a rigorous taxonomy, a classification system that would determine the exact boundaries of technical feasibility. SRI's solution was to completely separate the software from the hardware in their development planning. They defined this separation as a split between artificial intelligence, representing the brain functions, and robotics, representing the body functions. Isolating these two halves meant engineers could target specific computational bottlenecks independently, without needing to wait for the physical hardware to catch up. This approach produced the concept of modularity, where software and hardware modules are developed as interchangeable parts. SRI didn't design a single robot. They built the foundational architecture that allowed military systems to become modular. This diagram from the executive summary illustrates the central framework of the report, a unified model of artificial intelligence and robotics. The top section defines the brain, or the AI domain. The brain's exclusive function is interpreting incoming sensor data, reasoning through logic problems, and maintaining a digital world model. The bottom section defines the body, which operates entirely within the physics domain. The body relies on mechanical and electrical engineering to manage physical sensors that see and touch, and effectors that move and manipulate. Consider a diagnostic application of this model. If an autonomous unit fails to navigate a complex environment, how do you isolate the error? A body failure is purely physical. The treads grind to a halt in heavy mud and cannot generate traction. A brain failure is computational. The cameras register the mud, but the logic box fails to correctly update its world model to recognize that terrain as impassable. By establishing this unified model, SRI gave the Army a precise diagnostic tool to isolate exact bottlenecks. They could fix a software flaw without scrapping an entire vehicle program. This page outlines the initial scope of the project. SRI generated 100 specific application concepts for combat systems. Attempting to evaluate and fund 100 disparate robotics programs at once is a logistical impossibility. To sort the data, SRI filtered these 100 concepts down into 10 broad categories based on 3 specific engineering criteria. The most critical criterion was technological similarity. Machines were not grouped by their military mission. They were grouped by the shared software brain and hardware body modules they required. As shown here, 100 distinct ideas were successfully distilled into these 10 strategic categories. This taxonomy converted a sprawling list of disconnected ideas into 10 manageable, overlapping research pipelines. SRI then applied a gap analysis to test which of these concepts were actually buildable with early 1980s technology. This feasibility timeline split the proposals between current tech and systems that required deferment to the year 2000 and beyond. This list on page 4 identifies 4 candidate systems that could be developed immediately. 2 highly physical systems made the cut, the mine clearer and the tank ammunition handler. The engineering logic for their approval is clear. Both systems operate in constrained environments with limited variables, requiring only a simple world model to execute their tasks.
As seen in this hardware photograph, a mine-clearing vehicle relies heavily on specialized mechanical equipment rather than complex decision-making. Contrast this with the light-fighting sentry, which SRI deferred to the next millennium. An automated sentry faces a fatal tech gap. It requires generalized target identification and open environment navigation. Those capabilities were mathematically out of reach in 1982. The table of contents maps the cascading dependencies required for advanced systems like threat projection, illustrating exactly how far away the necessary software modules were. A machine's feasibility was never dictated by its mechanical complexity. It was dictated entirely by the computational complexity of the required AI brain. The final piece of SRI's development strategy was a proposal for true system modularity. This section on common modules shows that SRI advised building shared software blocks that could be used across multiple different chassis to save time and funding. The situation monitoring system serves as a primary example of a shared computational module. This single software logic block could be plugged into both a mine clearer and a threat projection unit. By utilizing common modules, the Army could continuously upgrade the digital brain of a machine over decades without having to rebuild the physical body. The core philosophical contribution of the 1982 report is its precision in defining exactly where AI ends and robotics begins. This recreated unified model provided a partitioned, actionable architecture.
It allowed engineers to map a vast array of specific subtechnologies, from tactile sensors to expert systems, into their correct operational domains. This strict taxonomy defined the research and funding priorities for the next 20 years of military innovation. This photograph captures the reality of that era: human engineers testing early physical hardware under these newly defined parameters. The 1982 SRI report successfully established the modular blueprint that separated military science fiction from achievable phased engineering.
In the early 1980s, the computing power required to execute basic logic occupied entire rooms of spinning tape reels and physical memory banks. Yet in May 1982, SRI International delivered this 324-page research plan to the U.S. Army. The objective of this study was rigorous and highly pragmatic: evaluate 100 theoretical combat applications and separate buildable engineering from science fiction. The military's operational demands were incredibly broad. They wanted systems capable of maintaining the momentum of continuous combat operations against complex threats. And they wanted machines capable of high-level cognition. The requests included entirely autonomous software, like a tactical threat projection system. But the most demanding requests were physical. Deep in the index sits an application called the Light Fighting Sentry, a fully automated, mobile robotic combatant. Determining the feasibility of a mobile sentry required a formal architecture defining how an artificial entity processes reality. Military robotics in 1982 forced a collision between two scientific disciplines that rarely overlapped. On one side was pure mechanical engineering, the physics of propulsion, treads, and moving heavy armor across unpredictable terrain. On the other side was pure computer science, the abstract domain of code, logic gates, and data processing. The gap between them was immense. You could mount a camera to a vehicle, and it would capture light, but the software running on terminals of the era had no mechanism to understand what that light represented. Solving this required a translation layer, a structured method to map raw physical inputs onto cognitive decision trees, and then route those decisions back into mechanical force. Before the Army could commission a single autonomous weapon, they had to adopt SRI's proposed framework for machine cognition, the unified model. The architecture begins at the exact points where a machine makes physical contact with the world. Sensing handles environmental intake, cameras, radar, and tactile sensors. Affecting handles physical output, manipulator arms, treads, and weapons. Directly above this hardware layer sits the software boundary. The interpreting module parses raw sensor data and extracts meaning, while the generating module takes abstract instructions and converts them into specific mechanical commands for the effectors. At the center sits the reasoning module. This is the strategic core where tactical planning and logic are executed. Enclosing all these cognitive functions is the most computationally demanding component of the entire architecture, the world model.
The world model is the machine's internal, constantly updating digital representation of the physical battlefield. Every piece of data must travel this exact pathway for any autonomous system to function. SRI used this structured workflow to audit the Army's requested arsenal. They condensed the 100 initial concepts into 10 distinct categories of military applications. We can see how the audit worked by running specific examples through the unified model. Take the division commander's quick data access system. This intelligence tool was designed to query databases and execute logic. It did not need to physically navigate a combat zone. By bypassing the sensing and affecting translation layers entirely, SRI concluded this system could be built with the technology available right then, in 1982. The same was true for the tank ammunition handler and the robotic mine clearer. These machines required heavy physical effectors, but their operations were strictly constrained. They performed repetitive mechanical loops, requiring minimal strategic reasoning or interpretation of complex environments. The model yielded a completely different result when testing the light fighting sentry. An automated sentry must simultaneously interpret continuous, chaotic visual data, execute strategic reasoning regarding threat targets, and generate complex physical movement across uneven terrain. The computational power required to constantly update a world model with that volume of sensory data simply did not exist. The unified model effectively sorted the Army's wish list, isolating immediate software and industrial tools from dynamic combat systems. Development of the Sentry was officially deferred until the year 2000. Discarding the robotic Sentry was a highly valuable diagnostic result. It pinpointed exactly where the scientific constraints were located. By identifying the failures within the unified model, SRI generated a precise map of 97 specific research tasks that required advancement. The physical mechanics were a relatively minor hurdle. The report lists only 6 tasks required to advance sensing and 5 to advance affecting. This chart visualizes the true bottleneck. Compared to the 11 physical tasks, SRI identified 73 specific cognitive tasks. 20 of those were needed just for computational vision and language interpretation. The deepest gap sat in the reasoning block, which demanded 45 distinct research tasks to make expert systems and action planning operational. This itemized list transformed an abstract desire for robot soldiers into a targeted funding checklist, directing Pentagon resources directly into foundational computer science. SRI also recognized that attempting to engineer a customized, standalone brain and body for all 100 applications would be economically impossible. Their solutions to this storing problem was strict modularity. The report states that both hardware and software modules could be common across multiple applications. An interpreting or reasoning module could be programmed once and then ported across different platforms, from a desktop terminal to an armored vehicle. The physical processors of 1982 were massive, rigid, and slow. The hardware was decades away from being combat ready, but the systems engineering framework used to evaluate it was structurally sound. SRI's study established a methodology for decomposing robotic complexity into discrete, swappable functions. By prioritizing the logical depth of software modules over pure hardware endurance, the 1982 audit defined the technical standard that continues to govern the development of autonomous systems.
This document is the May 1982 R&D Plan for Army Applications of AI and Robotics, compiled by SRI International. The military's initial demand was vast. Identify 100 blue sky applications where artificial intelligence could be deployed in combat and combat support. Assessing 100 of these undefined concepts without a formal engineering framework in place is an exercise in pure chaos. SRI faced a severe obstacle in 1982. The prevailing academic tendency at the time was to treat artificial intelligence as a software capability, operating completely divorced from the physical hardware of robotics. A disconnected computational brain operating in a vacuum has zero utility on a dynamic, unpredictable battlefield. SRI's solution was a unified cybernetic approach. They determined that any viable engineering roadmap had to inextricably link the machine's mind to its physical body. The first step in military R&D wasn't writing code. It was defining the exact anatomical relationship between a machine and its environment. This diagram is SRI's unified model of artificial intelligence and robotics. It permanently merged the two fields and became the rulebook for the entire study. At the bottom is the physical layer, consisting of sensing and affecting. These base functions are bound entirely by the raw laws of physics and mechanical engineering. Cameras require light, and mechanical arms require physical torque. Sitting above the physical inputs is the intermediate cognitive layer, interpreting sensory data and generating physical instructions. In the center rests the core decision engine, reasoning. Unlike the physical base layer, these three cognitive blocks are strictly computational and algorithmic challenges. All of these cognitive functions are encompassed by a single, massive bounding box labeled the world model. The world model acts as the ultimate bridge. It is continuously updated by the physical sensors to inform the computational reasoning. If a machine's internal world model desynchronizes from external physical reality, the entire loop breaks and the system collapses. This theoretical loop provided the brutal, unforgiving engineering filter required to evaluate the Army's long list of combat concepts. SRI took the Army's overwhelming list of 100 concepts and ran them through this filter. The first mechanism was categorization. They organized the scattered ideas by grouping them based on technological similarity and military function. This table details the resulting distillation. The chaos was compressed into 10 structured categories. These categories span the operational spectrum, ranging from purely passive information gathering down to active weapon systems. But an abstract category cannot be engineered, budgeted, or physically tested in a laboratory. To solve this, SRI executed a second filtering step. They selected one highly specific, concrete prototype to represent each of the 10 categories. The matrix translates those 10 broad categories directly into 10 specific prototype systems. The Brigade Mission Planning Aid serves as an example of a purely cognitive, software-driven prototype. Contrast that with the Light Fighting Sentry, a highly dynamic, physically complex machine designed to move through an active battle space. These 10 prototypes established a complete spectrum of ambition. They were perfectly staged to be stress-tested against the hard limitations of 1982 hardware. The appraisal phase projected the computing power and mechanical reliability required to actually build all 10 prototypes. The timeline fractured immediately. 6 of the 10 systems were completely disqualified from early development. This text lists the only 4 viable early start applications that passed the appraisal with then current technology. The survivors were the Mine Clearer, the Brigade Mission Planning Aid, the Tank Ammunition Handler, and the Division Commander's Quick Data Access System. We can see exactly why these 4 survived by mapping them back onto the logic of the unified model. The data access and planning systems succeed because they bypass physical effectors entirely. They exist only in the cognitive layer. The ammo handler and mine clearer succeed because their physical environments and movements are highly predictable and repetitive. Now, look at the failed Light Fighting Sentry, which required unconstrained mobility in an open environment. The computational load required for real-time vision processing, just to prevent a moving robot from crashing into an obstacle, was too immense for early 80s hardware. By the end of the appraisal, SRI had identified 97 distinct gaps in the technology base that prevented dynamic, autonomous combat. Full autonomy is impossible when a machine's physical environment changes faster than its internal world model can compute the updates. How does defense R&D proceed when facing 97 critical technology gaps that might take decades to solve? Building bespoke, monolithic prototype robots carries massive financial and technical risk. A custom robot becomes obsolete the moment the next microchip breakthrough happens. This conclusions page highlights SRI's primary systemic mandate. High-level system considerations had to be included in all future R&D planning. Specifically, they concluded that strict system integration and modularity must dictate the architecture. This is the proposed architectural solution of modularity. A reasoning software module can be seamlessly swapped for a faster, upgraded version without altering the physical chassis. This doctrine successfully isolates the rapidly evolving software layer from the slower-moving, expensive mechanical hardware layer. Modularity wasn't a manufacturing convenience. It was a required survival strategy against the threat of rapid technological obsolescence. The severe computational limits of the 1980s have been replaced by the era of modern neural networks and deep learning, yet the core physics remain. The cybernetic loop between sensing, reasoning, and effecting is still the immutable law of robotics. SRI's contribution was the engineering roadmap that defined the 97 specific technical hurdles between the concept and a working machine. They took 100 scattered concepts, filtered out the impossible, and established a highly focused R&D pipeline. Building combat-ready autonomy requires moving past conceptual lists and solving the hard mechanical and computational gaps identified in the unified model.
Today, artificial intelligence operates as a seamless layer of software, effortlessly driving everything from logistics networks to targeting algorithms. But back in 1982, the technological baseline was physically restricted. Computers were massive, mechanically rigid, and functionally isolated. Despite these severe hardware constraints, the U.S. Army looked at the speed of Soviet operations and identified a rapidly approaching bottleneck. They needed to field combat systems capable of operating independently on a continuous, highly lethal battlefield. To determine how to actually build that capability, the Army commissioned this document from SRI International. Released in May 1982, the report served as a mandate to map out a comprehensive research and development plan for military AI and robotics. The scope of the investigation was massive. SRI researchers analyzed the Army's operational needs and formally identified 100 distinct theoretical applications where automated systems could be deployed in combat and combat support. Before engineers could even begin drafting schematics for any of these ideas, SRI ran into a foundational logic problem. There was no shared scientific consensus on what a fully autonomous system actually required to function. At the time, the disciplines required to build a robot were strictly segregated. Computer scientists worked on the brains, processing logic in mainframes, while mechanical engineers focused entirely on the bodies, building servos, treads, and hydraulic linkages. SRI recognized that treating these fields as separate problems was a structural flaw. To solve the Army's challenge, the researchers explicitly collapsed the boundary between artificial intelligence and robotics. They engineered a unified architecture, a strictly defined functional blueprint that accurately outlined exactly how autonomous systems would be built for the next 40 years. This diagram is SRI's unified model of artificial intelligence and robotics. It maps the complete functional loop required to operate intelligently. At the bottom, we find the physical base. These two blocks represent the robot's body, beginning with environmental inputs. SRI defined sensing strictly as a hardware challenge. This is the mechanical process of gathering raw physics data, capturing photons, pressure, and sound waves from the battlefield. Researchers cataloged the hardware needed to capture data, prioritizing visual and tactile sensors. The direct counterpart is effecting, the mechanical output manipulating the environment. SRI categorized these effectors into discrete forms, breaking down requirements for robotic hands, arms, and legs. The direct counterpart to sensing is effecting. This is the mechanical output, where the system translates its internal energy into physical manipulation of the environment. An articulated arm and a camera lens do not make a smart machine. At this base level, they are simply dead mechanics and raw data. To be useful, the architecture requires a bridging mechanism. The physical body needs a way to translate real-world physics into digital logic, and to convert digital commands back into kinetic force. This brings us to the middle layer. These two blocks act as a digital nervous system, connecting hardware to the cognitive brain. First is interpreting. This software takes chaotic, unstructured physics data from sensors and organizes it into recognizable, discrete variables. Think of the gap between a camera sensor registering a grid of light and dark pixels and a software algorithm successfully interpreting that specific pattern as the silhouette of an enemy T-72 tank. On the other side of the loop is generating, which handles the exact reverse operation. It takes an abstract digital intent and expands it into the complex electrical commands required for movement. A logic command to move forward cannot just be sent to a piece of metal.
The generating layer computes the precise multi-joint kinematics and torque values needed to physically actuate a hydraulic leg or drive a motorized track. In 1982, writing the software for this translation layer was the most computationally expensive and difficult engineering hurdle the researchers faced. Once that sensor data is successfully interpreted into clean digital formats, it can finally be handed upward for strategic processing. By isolating, interpreting, and generating as discrete software steps, SRI clearly defined the technical gap separating a radio-controlled drone from an autonomous agent.
At the top of the diagram sits the cognitive core. This is the strict domain of artificial intelligence. The reasoning block governs the system's capacity to plan missions, monitor execution, and dynamically alter its actions based on interpreted data. Reasoning requires a world model. This is an internal, updating digital replica of the operational environment. True autonomy is achieved when a system compares incoming sensor interpretations against this model, calculating routes, assessing threats, and making tactical decisions without human input. SRI mapped the Army's 100 combat concepts into 10 standardized categories. The first 4 are software-heavy, straining the interpreting and reasoning layers. Contrast that with categories 5 through 9. These demand robust hardware, straining the generating and affecting stack to execute complex physical movements. Identifying exactly where a theoretical concept sits within this functional loop immediately dictates its engineering feasibility. Breaking tasks into specific logic nodes allowed SRI to pinpoint where the state-of-the-art fell short, exposing hard limits in early 80s processing and sensor resolution. SRI mapped military ambitions directly to a strict functional model. This gave the Army a surgical tool to dissect which concepts could be built immediately and which ones required decades of baseline research before they would ever see a battlefield. That precision was critical for R&D triage. The Department of Defense needed to separate projects with immediate tactical value from those rooted in academic theory. SRI determined only 4 specific applications were mature enough for prototype development using 1982-era technology. These passed the filter because their requirements aligned with existing capabilities. The Mine Clearer required highly constrained mechanics and basic sensors, demanding almost no theoretical leaps in interpreting or reasoning. Early development on semi-autonomous mine-clearing vehicles was already underway at the time, directly validating the accuracy of SRI's near-term model. Compare those to the applications categorized as long-range, such as the Light Fighting Sentry or the River Reconnaissance System. A robotic fighting sentry failed the feasibility test because its core function requires flawless, real-time world modeling to distinguish a hostile target from a friendly soldier. In 1982, that level of cognitive processing simply did not exist. By drawing these clear technological boundaries, the SRI report protected massive defense budgets from being squandered on unbuildable hardware. The feasibility matrix made it clear the immediate future of military automation was not going to arrive in the form of general-purpose humanoid infantry. It would begin with highly specialized, narrowly defined support systems. Buried in the conclusions of the report is a single system recommendation that effectively predicted the structure of the modern defense industry. In Item 11, SRI delivered a firm directive. Future military R&D must be built on system integration and modularity. Robotic systems will not evolve by forging new metal bodies. Instead, major advances will happen through the continuous upgrading of software modules. This is where the unified architecture proves its enduring value. The physical sensors and effectors can remain static, locked in as baseline hardware, while the interpreting, reasoning, and generating layers rapidly cycle through software iterations. Military hardware platforms are notorious for having life cycles that stretch for decades, but software logic scales exponentially with the speed of compute. Mechanical engineering of tank treads and servo motors has remained relatively stable over the last 40 years. Meanwhile, the fields of computer vision and machine learning have experienced explosive growth. This exact premise drives modern autonomous warfare today. Aging legacy airframes are continually updated and deployed with cutting-edge reasoning engines downloaded straight into their processors. The 1982 SRI report operates as the foundational doctrine for modern automated warfare. By recognizing that artificial intelligence and physical robotics are distinct nodes in a single modular loop, the researchers successfully architected the exact system structures we are building today.
By the early 1980s, defense planners realized that computing power was going to scale rapidly enough to begin automating the battlefield. To understand exactly what that required, the U.S. Army tasked the research institute SRI International to project the future of combat robotics. This document is the resulting blueprint. Delivered in May 1982, it established a technical framework for autonomous defense technology. The abstract outlines the sheer scale of the project. The researchers identified 100 distinct applications for artificial intelligence and robotics in combat and combat support. But military planners could not act on science fiction weapon concepts alone. They required a method to identify the specific technology gaps preventing deployment. In 1982, AI software and physical robotics were largely treated as separate, isolated fields of research. This separation often resulted in machines that could move but not adapt, or software that lacked the physical awareness to function in a chaotic battlefield. To build a multi-decade roadmap, SRI first had to define exactly how a thinking machine operates within physical space. Their solution was a thesis requiring the tight integration of cognitive brain functions and mechanical body functions into a single closed-loop system. This diagram outlines the result, their unified model of AI and robotics. It provided the architecture necessary to map abstract AI concepts directly onto mechanical constraints. By reverse engineering this diagram, we can see the exact requirements of 1980s systems engineering. Every intelligent system must begin with a physical connection to its environment. This connection is governed strictly by the laws of physics and mechanical engineering, independent of any software logic.
Establishing this theoretical baseline moved autonomous development from ad hoc experimentation towards standardized systems engineering. Starting from first principles, we isolate the robot's physical presence. Sensing represents the hardware responsible for capturing environmental data, the mechanical ability to see and touch. Checking the table of contents, we see the specific analog hardware SRI analyzed, including visual, tactile, and range sensors. On the other side is affecting, the hardware responsible for moving through the environment or physically altering it. Section 3.5 details the mechanical effectors SRI evaluated, such as robotic hands, arms, and legs. In 1982, these components faced severe limitations. Analog sensors were heavy, and early hydraulics were slow and mechanically fragile. No amount of elegant software logic can overcome a shattered visual sensor or a jammed mechanical actuator. Mastering this mechanical body was a strict prerequisite before any AI could be practically deployed. Connecting the physical world to the digital mind requires a translation layer. Interpreting is the software conversion of raw analog sensor data into contextual digital information. The primary challenge here was taking raw pixel arrays from a camera and computing them into functional machine vision. Filtering out unpredictable battlefield noise like smoke, debris, or electronic warfare during this interpretation phase requires immense processing power. Generating performs the inverse function, taking abstract system decisions and calculating the precise physical motor commands required to execute them. Generating continuous mobility control instructions over uneven, unpredictable terrain is incredibly complex math. At the time, microprocessors were simply too slow to perform this mathematical translation in real time. This middle layer acted as the computational bottleneck, where physical reality met the limits of early digital hardware. The highest architectural layer is where the system's reasoning resides. Reasoning handles the assimilation of interpreted data, active action planning, and continuous situation monitoring. It operates entirely within the constraints of the world model, the internal map and rule set the robot uses to understand its surroundings. Reasoning logic is useless without a reliable world model to provide situational context. With the model fully assembled, the system relies on a continuous closed data loop. Any processing latency at the reasoning level causes the physical machine to freeze or crash in the real world. The complexity of a system's required world model would ultimately dictate whether it could be built with 1982 technology. SRI took this theoretical model and applied it to 10 application categories for specific military roles. Mapping their findings creates a comparative audit. What was feasible with 1982 hardware versus what had to be deferred until the year 2000. Under point 10, they identify 4 candidate applications that could be developed immediately, including a mine clearer and a tank ammunition handler. These early start applications shared a common architecture. They operated from stationary positions or relied on highly structured, heavily bounded world models. However, point 13 shows that ambitious concepts like the light fighting sentry and river reconnaissance system were formally deferred. These were deferred because navigating dynamic battlefields requires unconstrained sensing and massively complex world models. While mechanical fabrication was maturing, 1982 microprocessors lacked the speed to fully render unpredictable environments in real time. This audit directly informed the final and most valuable deliverable of the SRI report. They quantified the gaps preventing those deferred systems from being built, itemizing them into a checklist of research tasks. The report mandates 12 specific tasks in computational vision, 16 in action planning, and 13 in expert systems. By overlaying military functions onto the unified model, they generated a precise, actionable roadmap for developers. In point 11, the researchers proposed that these systems should evolve through module replacement, especially by upgrading software modules. This early emphasis on software modularity anticipated the requirement for continuous, iterative updates in autonomous defense platforms. By isolating these bottlenecks, SRI's gap analysis aligned with the specific research trajectories that define modern robotics. The true foundation of complex engineering is having the rigorous discipline to acknowledge exactly what you cannot yet build. What started as a theory connecting brain functions to mechanical body parts resulted in a quantified 97-point checklist for future development. SRI's 1982 report established the systems-level analysis required to transition from science fiction concepts to an actionable engineering roadmap.
In 1982, researchers were handed an impossibly ambitious task: map the future of autonomous military robotics decades before the underlying technology even existed. The result was this document, delivered by SRI International to the U.S. Army. It provided a systematic R&D plan for integrating AI into combat vehicles. The mandate was massive in scope. The researchers evaluated 100 different theoretical applications of artificial intelligence and robotics. To understand the difficulty of this request, remember that computing in 1982 was defined by massive, tape-based mainframes. The idea of fielding artificial intelligence on a chaotic battlefield was entirely theoretical. The researchers had to look past science fiction concepts. Their immediate challenge was structuring a realistic, systematic research and development roadmap for hardware and software that didn't yet exist. Early engineers were blocked by a conceptual bottleneck, defining the exact boundary where mechanical engineering ended and computer science began. Historically, physical hardware, the robotics, and the logical software, the artificial intelligence, were treated as entirely separate academic disciplines. They didn't speak the same language. To build a functional military roadmap, SRI replaced the division between AI and robotics with a unified model that combined them. They proposed a unified model, a single first principles architecture designed to encompass the functions of any intelligent machine. Without a unified framework, evaluating 100 random vehicle concepts would be chaotic. By combining them, the military could map exact shared technological bottlenecks across completely different platforms. The report established a baseline axiom: an intelligent robot must execute 3 fundamental functions: think, sense, and effect. First is the machine's physical body. The sensing function, utilizing cameras, tactile sensors, and radar, is governed by physics and electrical engineering. The second part of the body is affecting. This covers movement, manipulation, arms, and treads, the domain of mechanical engineering. This physical hardware operates underneath the brain. The brain is strictly the thinking function executed by the computer, the isolated domain of artificial intelligence. By isolating the brain into its own distinct box, system planners could pinpoint exactly what cognitive software capabilities were missing for autonomous battlefield operations. Data flows upward, but raw sensor input, like pixels or radar echoes, is useless unless the machine can interpret what it means. Once interpreted, categorizing a shape as a tank, that data is fed into the machine's reasoning core to make decisions. At the apex of the brain is the world model. This is the machine's internal digital representation of physical reality, constantly updated by its reasoning. Once the system reasons against its world model, it must generate a specific action plan. Finally, that generated plan is translated back into physical reality through the hardware effectors, completing the architecture. This specific loop, sense, interpret, reason, generate, and effect, creates a universal measuring stick. It allows engineers to evaluate the feasibility of any autonomous system, regardless of its shape, size, or lethal purpose. SRI took the 100 initial combat concepts and ran them through this new unified model. Instead of categorizing the ideas by vehicle type, like putting all tanks in one group, they grouped them by technological similarity, identifying exactly where their specific bottlenecks were located within the brain and body. This table details the results, showing how the 100 raw concepts were successfully boiled down into 10 fundamental, actionable application categories. For example, if an automated ammunition loader and a reconnaissance drone both need to visually process their environment, they share an interpreting bottleneck. Both platforms require the same underlying computational vision research to function. Identifying these shared gaps allowed the Army to prioritize foundational technology elements that could be reused across multiple different platforms. The report defined a strict feasibility spectrum. Some systems could be built immediately in 1982, while others would have to be pushed out to the year 2000. Looking closely at their findings, the Mine Clearer emerges as an immediate candidate, an application that could be developed with current technology. Through the lens of the unified model, the reasoning is clear. Its physical task is simply driving forward. Its world model and reasoning requirements are low, requiring only basic binary sensing hardware to locate metal in the ground. Compare that to a far-term concept they deferred to the year 2000, the light fighting sentry. A sentry requires a massive computational leap in the interpreting block just to visually distinguish a friendly soldier from an enemy target. It also demands highly complex reasoning capability to calculate tactical threat projections and make autonomous firing decisions in real time. The 1982 report laid bare a core reality. The mechanical hardware, the tanks, guns, and motors already existed. The true research gap preventing autonomous warfare resided within the specific software modules of the unified model's brain. To navigate this multi-decade technology gap, SRI delivered its strategic recommendation, modularity. Practically, this meant the Army should build a physical chassis today, activating only basic sensing and effecting hardware.
As computer science advances, engineers can swap out those empty software modules with smarter, complex versions without having to rebuild the entire tank or sentry from the ground up. This modular approach mitigates long-term risk. It prevents massive physical hardware programs from becoming completely obsolete before the artificial intelligence is even ready to deploy. Ultimately, the 1982 SRI report provided the complete, systematic, and theoretical blueprint for exactly how to engineer these autonomous weapons. The document shifted the engineering focus from the mechanical capabilities of the machine's body to the architectural requirements of its mind. Foresight in systems engineering relies on building modular architectures that can incorporate new software capabilities as they are developed. In the early days of automation, computer science and mechanical engineering were largely siloed disciplines. Researchers developing artificial intelligence focused on the cognitive brain, while mechanical engineers built the physical body. In May of 1982, the U.S. Army tasked SRI International to bridge this specific divide for future combat operations. The mandate was to create a comprehensive research and development master plan that evaluated exactly how these emerging technologies could be practically applied on the battlefield. The immediate problem SRI faced was structural. There was no standard systems engineering methodology to evaluate cognitive software and physical hardware as a single, inextricably linked system. To judge which military applications were actually feasible to build, SRI realized they had to design a unified theoretical framework from scratch. To construct the autonomous systems of the future, defense planners first had to define the exact theoretical constraints of how a machine thinks and acts simultaneously. SRI's initial data collection identified 100 specific theoretical concepts for AI and robotics in combat and combat support.
To filter this massive list, researchers applied a strict methodological funnel, analyzing each of the 100 concepts across 6 distinct viewpoints: threats, units, equipment, functions, environment, and personnel. This rigorous analysis allowed the team to collapse the 100 scattered concepts down to a highly structured list of just 10 broad categories. These final 10 categories were not divided by traditional military combat functions, like infantry or artillery. They were grouped by technological similarity, meaning the machines in each category required advances in the exact same R&D areas. To determine if these 10 hardware examples could actually be built, SRI now had to process them through their newly invented theoretical framework. Identifying a military need is only the first step. To build these systems, SRI had to translate battlefield requirements into a structured format that engineers could use to measure technical feasibility. This diagram represents SRI's unified model of artificial intelligence and robotics. The bedrock of this architecture is the 2 physical interfaces connecting the machine to reality. Sensing encompasses the physics-based hardware, visual, tactile, and range sensors actively gathering raw environmental data. Affecting covers the mechanical engineering domain, the mobility chassis and manipulating arms responsible for executing physical actions. But raw physics data is useless to a computer without an intermediate translation layer.
The interpreting node translates unstructured analog inputs, like raw camera pixels or LiDAR bounces, into actionable digital information through computational vision. The generating node reverses the process. It takes abstract digital commands and translates them into the specific motor currents required to drive the effectors. The physical body of the robot relies entirely on these specific translation layers to communicate with the brain. Above the translation layer sits the cognitive center of the architecture, the domain of pure artificial intelligence. The reasoning node handles the core AI tasks, assimilating incoming information, drafting expert action plans, and monitoring situations. Enclosing this entire cognitive stack is the overarching element that defined the true bottleneck of 1980s computer science: the world model. An intelligent robot must maintain an internal, continuously updated digital representation of its surrounding physical environment. The reasoning layer cannot calculate a viable plan of action if the internal map of reality it relies on is outdated or flawed. Autonomy is constrained not by mechanical strength or raw processing speed, but by the ability to accurately maintain and navigate this internal world model. This plot illustrates how SRI used the constraints of their unified model to grade the 10 military application examples on a timeline of near-term versus long-term feasibility. They identified several systems that could be prototyped using existing 1982 technology, specifically pointing to a mine clearer and a tank ammunition handler. A tank ammunition handler operates inside a highly constrained static physical space. Because the environment is fixed, the robot's required world model is extremely simple. It demands very little active processing from the interpreting and reasoning layers. Contrast this with the systems marked for long-term deferral, such as the light fighting sentry and the river reconnaissance system. These systems operate in chaotic, highly unstructured outdoor environments. Differentiating between friend, foe, and moving terrain requires a hyperdynamic world model and advanced computational vision. That technology simply did not exist, leading SRI to recommend these projects be deferred until the year 2000. The boundary of technological feasibility lies directly on the edge of environmental predictability. A chaotic real world places a heavier cognitive load on the machine. Viewing AI and robotics through this unified lens led SRI to their most important R&D conclusion. They explicitly warned the Army against building siloed robots. It made no sense to fund a unique brain for a tank and a completely separate unique brain for an infantry sentry. Because the unified model broke autonomy down into discrete, isolated computational nodes, SRI recommended focusing entirely on universal software modules. If you treat the robot as a modular stack, a single R&D breakthrough in a computational vision module could be integrated across dozens of different vehicle platforms. SRI's master plan was built on this concept of commonality, creating a modular architecture where specific software improvements could be shared across the entire robotic fleet. This 1982 framework accurately identified the exact bottlenecks that would constrain autonomous systems development for the next 40 years.
Today's self-driving cars and autonomous drones still operate on these exact foundational principles: perception, cognition, and action. The core engineering challenge remains exactly what SRI charted: safely updating the internal world model in a chaotic, unpredictable environment.
SRI mapped the roadmap for autonomous warfare when the required hardware constraints were still decades away from being solved. Long before the microchips were fast enough, and before the sensors were sharp enough, the theoretical architecture for the machine had already been rigorously defined. By the early 1980s, the development of physical Cold War military hardware and the sterile theoretical realm of computer science existed in entirely separate worlds. The engineering of a machine's body, its hydraulics, treads, and armor, was treated as an isolated discipline from the development of its brain, the algorithms governing artificial intelligence. Systems like the IBM System 370 represented the era's peak computational power. They were massive, stationary machines, excellent at processing static data, but completely disconnected from mobile, physical interaction. Inside these mainframes, early AI was largely confined to text-based expert systems and theoretical logic. It solved enclosed puzzles, blind to the outside environment. But the military recognized that deploying autonomous weapons, machines capable of navigating battlefields and operating armaments without human input, would require merging these two disparate fields. The problem was architectural. Without a unified taxonomy to describe how a software logic engine should communicate with a mechanical chassis, integrated combat machines could not be built. In May 1982, SRI International delivered a comprehensive study to the U.S. Army designed to solve this architectural disconnect. The document's core objective was to chart a precise, multi-decade research and development pipeline to move AI and robotics out of the theoretical phase and into active combat deployment. The researchers began with a massive data collection effort, documenting 100 theoretical concepts for automated combat and support systems. SRI subjected these 100 concepts to a strict triage process. They cross-referenced every idea against 6 rigid military realities, evaluating threats, unit operations, functional requirements, and harsh environmental variables. By forcing abstract code through strict operational filters, the report created a mechanism that required software developers and mechanical engineers to work within a single, unified framework. The researchers proposed a specific structure to bridge the brain-body divide. The boundary begins with the world model. It is an entirely digital software representation of the physical battlefield outside. At the apex sits the reasoning module. This is the cognitive engine. Reasoning is the software logic responsible for action planning, assimilating incoming information, and making tactical decisions. It operates as the highest order controller. Every other process in the machine exists either to supply data to this module or to execute its commands. Because a reasoning engine evaluates logic and cannot process raw physical chaos directly, it requires the strict boundary of the world model to organize unpredictable environmental factors into calculable variables. To connect reasoning to reality, decision layers are placed beneath it. On the input side, the interpreting module converts raw data into structured concepts. On the output side, the generating module translates abstract decisions into specific executable commands. These two software modules act as the required cognitive bridge, converting pure algorithms into instructions for physical movement. Moving outside the digital boundary brings us to the actual physical hardware. Sensing hardware, like cameras and rangefinders, gathers raw environmental data, feeding it upward. Meanwhile, affecting hardware receives commands and executes physical actions. This completed loop illustrates a critical vulnerability. A failure in a single node, like a blinded camera, means the interpreting module receives no data. The world model collapses, and the entire thinking and acting cycle paralyzes. By mapping the machine as an interdependent loop, SRI forced the military to recognize that investments in AI logic were useless without equal investments in sensor and mechanical research. With the theoretical architecture established, SRI used the unified model to organize real military technology. They filtered their initial 100 concepts into 10 distinct application categories, grouping them by their technological similarity and the engineering demands they placed on the model.
For example, software-heavy concepts like human equipment interface aids required immense computational power, stressing the interpreting and generating language nodes. Contrast that with hardware-heavy systems, like a robotic light-fighting sentry. That application placed extreme stress on the bottom of the loop, requiring major advances in sensing and affecting hardware. The ultimate goal was for these categories of technology to augment or replace the heavy physical combat equipment already deployed, such as the M1 Abrams. Grouping theoretical designs by where they stressed the unified model provided the Army with a highly efficient roadmap for R&D investment. The researchers then audited the 1982 technology base to determine which of these hardware concepts could actually be manufactured. Their gap analysis revealed that the current state-of-the-art suffered from 97 specific research gaps across the various domains of the unified model. The heaviest bottlenecks identified in the report existed in computational vision and action planning. The software simply could not process visual data fast enough to map a physical environment accurately. Because of these severe limitations in the interpreting nodes, SRI advised the military to defer complex long-range mobility concepts like autonomous river reconnaissance systems until the technology matured. Defining the exact engineering delta between theoretical ambition and actual 1982 capability proved to be the most valuable function of the plan. The triage process did, however, yield immediate results. Out of 100 original ideas, SRI identified 4 candidate applications capable of immediate development: a mine clearer, a brigade mission planning aid, a tank ammunition handler, and a quick data access system. These systems survived the audit because they were evolutionary. They bypassed the need for high-level computational vision and relied instead on constrained, highly specific logic circuits. The engineering demands for the mine clearer were so achievable with existing hardware that the Army had already started its development before the SRI report was even published. The 1982 SRI report succeeded by proving that physical robots are merely the physical outputs of a unified cognitive loop. By creating an architecture that treated sensors, logic, and mechanics as one continuous system, the document established the engineering standard that guided the next 40 years of military automation.
Back in 1982, standard computing meant typing commands into a basic green screen terminal on a cathode ray tube monitor. Yet inside the Pentagon, defense planners were already drafting requirements for fully autonomous, thinking combat robots. To bridge the gap, the U.S. Army commissioned SRI International. Their deliverable was this document, published in May 1982, a comprehensive R&D plan. The mandate was massive: identify 100 distinct ways AI and robotics could be deployed across operations. The researchers proposed highly ambitious, futuristic concepts, formally logging entries like the light-fighting sentry into the official record. But listing theoretical vehicles doesn't give engineers a way to build them. The military needed a strict, actionable framework to organize research for systems that defied the physical limits of 1980s hardware. The core systems engineering problem was establishing a legitimate R&D pipeline for capabilities, like advanced computational vision, that did not yet exist. SRI's solution was to avoid focusing on the physical shape of the final vehicles. Instead, they mapped out a universal systems architecture. They achieved this by strictly decoupling the machine's cognitive brain from its mechanical body. To solve the R&D problem, SRI engineered a unified model, a strict framework integrating diverse AI and robotics research into a single, modular architecture. Understanding this 1982 blueprint provides the precise coordinates for how all contemporary robotics research is categorized and structured today. This diagram is the original unified model proposed in the SRI report. It reduces any theoretical robot down to a set of core functional blocks. Starting at the bottom are physical capabilities. Sensing gathers data, while effecting controls movement. Above sits the cognitive brain, interpreting, reasoning, and generating within the world model. The engineers drew a hard boundary through the middle: physics below, artificial intelligence above. This separation of concerns allowed software logic to be developed entirely independently of the hardware chassis it would eventually command.
For a machine to execute an autonomous action, data must flow through this architecture in a continuous loop, starting with hardware gathering raw environmental data. The feed flows upward from sensing to the interpreting module, becoming digital objects that populate the world model. The reasoning engine queries this map to make a decision, passing it to generating, which sends commands down to the effecting hardware to execute movement. If any step breaks, autonomy is lost. Without the complete loop operating in real time, the machine defaults to being a simple remote-controlled tool. SRI filtered 100 concepts down to 10 specific examples. Why were some ready for immediate development, while others faced a 20-year delay? The answer is processing load. Take the mine clearer, identified as buildable with 1982 technology. When mapped onto the unified model, the mine clearer's processing loop is short. It only requires basic sensing, like a magnetic metal detection sweep, and low-level reasoning, specifically the logic to stop and drop a flag. Compare that short loop to the light-fighting Sentry, a platform that the engineers concluded must be deferred until at least the year 2000. A Sentry robot creates massive computational bottlenecks in the cognitive layer. Interpreting complex visual data to reliably identify friend from foe, and reasoning out dynamic fire control plans required processing power that simply did not exist. By running every concept through the same architecture, the unified model stripped away subjective guesswork and replaced it with objective, quantifiable engineering constraints. The 10 specific vehicle concepts outlined were never meant to go straight to the assembly line. They were theoretical thought experiments designed specifically to generate data. The true deliverable of the project was to identify the exact technological gaps preventing the unified model from functioning in the real world. SRI produced a concrete R&D plan that broke the required fundamental research down into exactly 97 specific, actionable tasks. These 97 research topics mapped perfectly to the individual nodes of the unified model, targeting isolated weaknesses in computational vision, language generation, and mobility control. This granular task list allowed the military to deploy funding precisely where it was needed, targeting a specific computer science algorithm or a mechanical actuator, rather than throwing a massive budget at a generic robotics program. This component-level view led to the most important long-term engineering directive in the 1982 report, the absolute necessity of modular design. The engineers understood that artificial intelligence software would evolve at a much faster rate than heavy mechanical hardware. Therefore, the systems had to be hot-swappable. The researchers explicitly concluded that the evolution of these military systems had to occur by means of module replacement, specifically relying on the continual upgrading of software modules over time. The legacy of the 1982 SRI report lies in its rigorous systems architecture and the pragmatic way it forecasted technology development. By strictly isolating hardware from cognitive processing, these engineers provided the precise architectural coordinates for the autonomous systems we are currently deploying. Planning for the future of technology is rarely about guessing the final shape of the product. It's about engineering the fundamental architecture that makes the product possible in the first place.
In 1982, the U.S. Army was reaching a technical bottleneck. Military planners realized that tactical supremacy would soon depend on the speed of autonomous control. But the science required to build these weapons was siloed. At the time, artificial intelligence was strictly a computer science pursuit. It was restricted to large mainframes processing abstract logic, a disembodied brain disconnected from the physical environment. Conversely, robotics was a pursuit of mechanical and electrical engineering. It focused on moving chassis and industrial arms, a physical body with no capacity for independent decision-making. This academic divide created immediate friction for military engineers. They were attempting to build autonomous weapons, but the underlying disciplines lacked a common language to integrate logic with physics. Achieving autonomy required bridging these isolated fields to engineer a single, continuous cybernetic loop. The search for a coherent automation strategy fell to the U.S. Army Engineer Topographic Laboratories at Fort Belvoir. In May 1982, Fort Belvoir commissioned a sweeping study from SRI International to map the future of combat robotics.
The scope of SRI's mandate was to identify exactly how artificial intelligence could automate both direct combat and combat support over the coming decades. The resulting report made a significant departure from the era's academic norms. It formally rejected the separation of AI and robotics. By creating a unified model of intelligence and mechanics, SRI provided a systems engineering blueprint that allowed the military to finally define the specific technical components of an intelligent robot. The engineering challenge was mapping human cognitive and physical functions into a strict digital framework. This chart shows the baseline physical layer of the machine. This is how the system receives data and acts on its environment. Sensing encompasses visual, tactile, and range detectors. Effecting encompasses the physical mobility and robotic arms required to manipulate the world. Raw physics data is useless to a digital brain without conversion, which requires a translation layer. Interpreting translates that physical input into digital understanding. Generating works in reverse, converting digital choices back into physical kinetic commands. At the top sits the cognitive layer, the machine's brain, where the actual autonomous choices are made. Reasoning is the software responsible for task planning, monitoring, and decision-making. To make logical predictions, this reasoning occurs inside a world model, the machine's internal simulation of the battlefield. This architectural schematic is the historical model drafted by SRI in 1982. It provided the Army with its first formal definition of an intelligent system. Once the unified model was established, SRI used it to analyze all possible facets of Army combat operations. Researchers documented exactly 100 theoretical applications for this new cybernetic loop. But having 100 disparate concepts creates a challenge for R&D funding and procurement. To organize this, SRI filtered the concepts based on technological similarity, grouping the theoretical weapons by which specific parts of the unified model they stressed the most. This distilled the 100 concepts into 10 categories of application, such as situation assessment systems, expert advisors, and system controllers. This taxonomy transformed high-level brainstorming into a structured defense acquisition program. The computational limits of the early 80s were severe. Maintaining a complex, real-time world model in the middle of combat was mathematically impossible on the hardware of the time. SRI divided their concepts between systems that required future breakthroughs and those that could be built with existing technology. Highly complex, long-range concepts like a light-fighting sentry or a river reconnaissance system were deferred until the year 2000. Instead, they proposed 4 early start applications. These had limited capabilities and could be developed without advancing the fundamental technology base. These early systems focused on contained, specific loops. A tank ammunition handler didn't need open-ended navigation. It only needed to move heavy artillery from a rack to a breech. Prioritizing these limited systems allowed engineers to gain institutional support while slowly building the military's underlying AI technology base. The military faced a dilemma. Hardware takes years to field, but computer science improves exponentially. A robot finished in 1988 risked being obsolete upon arrival. To solve this, the report offered its ultimate strategic recommendation: system integration and modularity. Because the unified model established a standardized architecture, common functional software modules could be shared across different hardware platforms. By standardizing the architecture, the military could upgrade a robot's intelligence by swapping out its software interpreting or reasoning modules as computing power improved. This dictated a research structure where tasks were isolated into specific modules, like computational vision or expert systems, rather than trying to build one monolithic machine. The SRI plan provided the framework to decouple physical hardware from software development. This modularity ensured that as computing power improved, the Army's autonomous systems could be upgraded through their software, rather than requiring the total replacement of the machines themselves.
Modern autonomous systems process massive amounts of unstructured battlefield data in real time to navigate complex environments. But in the early 1980s, computing hardware was defined by expansive mainframe cabinets and severe processing constraints. Neural networks capable of navigating the physical world did not exist. Despite this, in May 1982, the U.S. Army tasked SRI International with creating a foundational research and development plan for integrating artificial intelligence and robotics into combat.
This is the resulting official report. It serves as a historical record of the monumental task the researchers faced. The team had to plan the architecture for autonomous machines decades before the microprocessors existed to fully run them. To determine what could realistically be built, SRI avoided science fiction. They engineered a strict theoretical architecture that mapped the relationship between how a machine ingests data, thinks about it, and acts upon the physical world. Cold War pressures demanded systems capable of sustaining high-momentum, mechanized combat operations. At the time, the dominant AI paradigm was the expert system. These systems relied entirely on rigid, pre-programmed if-then rules, rather than adaptable machine learning. Expert systems worked well for retrieving data in stationary, controlled settings. They were catastrophically insufficient for a machine trying to navigate the chaos of a moving battlefield. Previous military R&D failed because it frequently conflated the software of artificial intelligence with the physical hardware of robotics, leading to disjointed funding and failed prototypes. SRI bypassed this funding trap by establishing a comprehensive systems-level blueprint. They completely decoupled physical hardware from cognitive software. Without a strict conceptual boundary separating what a machine senses from what it thinks, the Department of Defense risked wasting millions on research bottlenecks they couldn't actually solve. To create this boundary, SRI built the Unified Model of Artificial Intelligence and Robotics, the foundational blueprint for all subsequent analysis in the report. This original diagram validates the historical presence of the model directly in the executive summary. At the bottom sits the physical body layer, the mechanism for sensing incoming data and affecting, taking physical action. Above this physical layer sits the cognitive brain. Raw data flows upward into the interpreting node, where the machine organizes the input. That structured data is then passed up to the core logic center, the reasoning node, where the system evaluates options and makes a decision. Once a decision is made, the system formulates a specific physical command through the generating node, passing the instruction back down to the effectors. Enclosing all of these cognitive functions is the most critical and resource-intensive component of the architecture. The world model is the machine's internal map of reality, a dynamic, constantly updating computational representation of the chaotic battlefield environment. This model successfully proved that robotics and AI were a single, interdependent, closed-loop system of data ingestion and physical actuation. The Army needed actionable R&D that could transition from academic models into field-deployable prototypes. This page outlines SRI's methodological approach, combining environmental constraints and threat assessments to derive exactly 100 potential combat applications. Building 100 bespoke robots would create a massive maintenance and supply chain burden for active units. To streamline the engineering, SRI grouped these 100 concepts down into 10 fundamental categories based purely on their technological similarities. This list charts the final 10 categories, pairing them with specific detailed examples. For example, the physical task of loading heavy shells into a main gun becomes a handling support system. By focusing on technological similarities, SRI realized that a single cognitive breakthrough could provide the software foundation for multiple different downstream weapon systems. Applying the unified model to these 10 examples immediately exposed the severe compute limitations of 1982. Out of all the detailed examples, SRI determined that prototype development could be started on only 4 with contemporary technology. We can use the unified model to explain exactly why these 4 were viable in the short term. Stationary systems like the tank ammunition handler operate in static, predictable environments. They require intense physical affecting, but a very small world model to calculate their surroundings. This sharply contrasts with long-range concepts like the light fighting sentry and river reconnaissance system. The report concluded those had to be deferred to the year 2000. Dynamic navigation and hostile target identification in a fluid environment place a massive computational load on the system. The point of failure was the interpreting node. The hardware lacked the capacity to process unstructured visual data into logic. The unified model served as a diagnostic tool, proving exactly why a robotic machine gun sentry couldn't be built with 1982 processors. The report's final recommendation was to establish a fundable, fundamental technology base. This breakdown maps 97 specific research topics directly to the nodes of the unified model. A heavy concentration of tasks was required in computational vision and action planning, far outweighing the basic physical manipulation requirements. SRI's ultimate architectural strategy to bridge this technological gap was modularity. The military was advised to build static physical architectures where cognitive software modules could be swapped and upgraded as algorithms improved over coming decades. Software-defined capabilities constantly updating within static hardware is exactly how modern technology and autonomous vehicles operate today. The 1982 SRI report is a rigorous piece of systems engineering. It established the framework for the modern battlefield by acknowledging its own hardware limitations and defining the specific computational bottlenecks that became the focus of the field.
Today, military artificial intelligence is debated as a ubiquitous, rapidly advancing reality. But 40 years ago, the concept was trapped in an academic wilderness, constrained by the physical limitations of spinning magnetic tape and room-sized processors. In 1982, the U.S. Army faced a distinct engineering problem. They needed to translate the theoretical math of AI into a practical, physical roadmap for combat. This document is the resulting R&D plan for Army applications of AI and robotics, a foundational blueprint produced by SRI International. Commissioned by the Army, researchers targeted ground warfare, seeking places where automation could improve frontline combat and rear echelon support. The mandate was broad. Researchers identified exactly 100 distinct applications where this technology might be deployed. Mapped out, a pattern emerged. The key technology elements required to build them were relatively small in number and highly overlapping. SRI avoided speculative traps by applying a disciplined systems engineering approach to every proposed machine. This approach translated vague military doctrine into a hard, unified cybernetic architecture. By cataloging the precise technological gaps of 1982, SRI established the first true engineering matrix for automated warfare. Before the Army could write a single line of code or bend a piece of steel, researchers had to formalize a boundary. They had to define precisely where mechanical engineering ends and actual intelligence begins. This diagram shows the report's foundational framework, a unified model of artificial intelligence and robotics. At the bottom of the structure are sensing and affecting. These are physical hardware problems, governed by the laws of physics and mechanics, encompassing optical lenses, tactile sensors, and mechanical arms. Above them sit interpreting, generating, and reasoning. This upper tier represents the cognitive computation, which is the exclusive domain of artificial intelligence. These cognitive nodes are entirely contained within the world model, representing the machine's centralized internal understanding of the physical environment around it. To force this theoretical model to function in reality, SRI evaluated the state of computing in 1982 and isolated exactly 97 specific research gaps that needed to be solved. The list is stark and precise. They required 12 distinct research tasks to achieve computational vision, 10 distinct tasks for language generation, and 16 tasks dedicated entirely to action planning. This model stripped the perceived magic away from machine intelligence. It reduced the daunting concept of automation into a finite, manageable checklist of computational hurdles. But how exactly does a clean, theoretical cybernetic architecture map onto the chaos and friction of an active battlefield? SRI analyzed operational military environments to filter their 100 potential concepts down into 10 distinct application categories. Physical combat support functions translated directly into hardware-heavy concepts, like a dedicated tank ammunition handler, relying heavily on the affecting nodes at the model. In contrast, cognitive, command-level operations dictated systems that bypass physical robotics entirely, creating a purely digital brigade mission planning aid. They also detailed pure data analysis tools like a tactical threat projection system, which would leverage the interpreting node to predict enemy movements based on massive incoming datasets. The breadth of these systems covers the entire operational spectrum, spanning from physical frontline robotics exposed to enemy fire to rear echelon software advisors running on secure servers. Every proposed system underwent a rigorous feasibility check that evaluated necessary physical design constraints, organizational distribution, and the exact software technology gaps required to build it. This categorization matrix bridged a massive communication divide, finally giving military commanders and civilian software engineers a shared, precise language for technological development.
Yet, mapping out 100-point wish lists is a common trap in military contracting. How did SRI prevent this R&D plan from turning into an unfundable compilation of science fiction? They instituted a rigid feasibility timeline, grounded entirely in the proven technological limits of 1982. This scatterplot chart illustrates how they mapped proposed systems against the available science. Highly complex autonomous combat systems, like a robotic light fighting sentry requiring rapid target identification, were explicitly deferred past the year 2000. Long-range dynamic environmental navigation programs, like the River Reconnaissance System, were similarly benched for future generations. The hardware simply lacked the capacity. Instead of waiting decades for processors to catch up, the researchers identified 4 evolutionary systems that could be initiated immediately with existing technology. The mine clearer served as the prime example of an immediate, physically achievable application, relying heavily on mechanical force rather than complex software perception. These 4 candidate systems were prioritized because their immediate operational benefits heavily outweighed their developmental risks. True strategic research requires the discipline to separate immediate engineering viability from long-term foundational theory. This phasing created a new structural problem. If the Army builds a rudimentary, hard-coded robotic system in 1982, how do they prevent it from becoming entirely obsolete by 1990? The report answered this with its ultimate architectural insight: modularity. Because all the categorized systems were built upon that shared unified model of sensing, reasoning, and effecting, they were designed to share underlying components. A computational vision algorithm developed to help an ammo handler recognize artillery shells could eventually be ported over to upgrade the optics of a mine clearer. This framework allows engineers to swap out an outdated optical sensor or slot in an upgraded software module without having to scrap and redesign the entire robot from scratch. This principle actively fought against the military's habit of building bespoke, isolated machines that couldn't communicate. This modular mandate created a standardized framework for military procurement, ensuring that new software could be integrated into existing platforms. The legacy of the 1982 SRI plan is the establishment of a common modular architecture of perception and reasoning, a structural blueprint that still drives military AI today.
In the early 1980s, the public envisioned military robotics strictly through the lens of science fiction, humanoid machines navigating combat with complete autonomy. But the United States Army had a practical problem. They needed to cut through the theoretical hype and establish a rigorous acquisition logic to determine what was actually buildable with existing hardware. In 1982, the Army Topographic Laboratories at Fort Belvoir tasked SRI International with generating a definitive, objective technology roadmap. The resulting document is this text, the R&D Plan for Army Applications of AI and Robotics. SRI was already running early laboratory prototypes, giving their research team the necessary engineering background to separate software theory from physical reality. Looking back, this text accurately isolated the exact computational and physical bottlenecks that still constrain autonomous systems today. To build the roadmap, the research team began by crowdsourcing 100 different theoretical applications for artificial intelligence across combat and support roles. But a raw list of 100 concepts is unusable for defense procurement, so SRI instituted a precise categorization system. They filtered ideas using 3 strict criteria: technological similarity, a recognizable military use, and comprehensive coverage of combat functions. This process compressed the data. 100 scattered hypothetical ideas passed through the filter and emerged as 10 distinct functional archetypes. This table lists the 10 concrete examples chosen to represent those categories, scaling from basic data retrieval networks at the top down to autonomous frontline systems like the light fighting sentry. Categorizing the concepts was only the organizational hurdle. The technical challenge was determining which of these 10 machines could survive physical deployment with 1982 technology. To estimate development timelines, SRI first had to mathematically define what an intelligent robot actually is. They established a baseline. Artificial intelligence and physical robotics cannot be evaluated as separate R&D tracks. The brain and the body are mutually dependent. This diagram is the original schematic they used to map that relationship, a unified model of artificial intelligence and robotics.
Internal functions are software interpreting data to reason a plan. External functions are hardware, sensing the environment and moving effectors. The system needs a continuous feedback loop. Sensors must feed data to the brain, which continuously issues commands to the effectors. Processing power alone does not equal intelligence. True autonomy requires the seamless integration of observing a physical space and effectively acting within it. Applying this unified model to the 10 prototypes immediately revealed a divide in development timelines. This section of the report identifies only 4 applications as feasible with existing 1982 technology: a mine clearer, a planning aid, an ammunition handler, and a data access system. The planning aid and data access system were purely software-based. They functioned solely within the reasoning phase and didn't require physical effectors to close the loop. The other 2, the tank ammunition handler and the mine clearer, did involve physical movement, but they operated in highly constrained, mathematically predictable environments. By contrast, systems intended for open deployment were explicitly deferred. The report notes the light fighting sentry and river reconnaissance system required advanced mobility, navigation, and real-time target identification. This leaves a technical division. Software planning aids could be engineered immediately, while an automated frontline sentry would remain unbuildable for decades. The roadblock was the physical reality of the battlefield. The military operates in unstructured environments where terrain, lighting, and obstacles change continuously. Applying the unified model to a frontline sentry reveals its structural failure. Early cameras generated massive, noisy data. In dynamic environments, this raw input overwhelmed interpretation, breaking closed-loop autonomy. Unable to update its world model, the connection to physical effectors severs completely. SRI diagnosed that solving real-time computer vision and dynamic mobility would require long-range foundational research in physics and computer science before a working prototype could even be attempted. Recognizing that fully autonomous robots were impossible at the time, SRI advised the Army to stop trying to procure complete, monolithic sci-fi weapons. Instead, their alternative strategy broke the required technology down into discrete research tasks, isolating specific gaps like computational vision and action planning. The strategy was modularity. By developing isolated, interchangeable software and hardware blocks, a vision module and a navigation module could be combined to build a functional mine clearer today. Decades later, as technology improved, those exact same modules could be continually upgraded and combined with a weapons block to finally construct the deferred light fighting sentry. This framework ensured that research budgets generated a compounding, reusable technology base, rather than being sunk into brittle prototypes that failed the moment they hit the field. The 1982 SRI report established the precise development roadmap that the defense industry would follow for the next 40 years. The report identified the primary bottleneck of advanced AI as the physics of closing the loop between digital intent and mechanical action. Compressing 100 sprawling ideas down into 10 archetypes and then isolating the exact technological gaps provided a rigorous method for managing complex programs. You do not buy an intelligent machine off the shelf. You systematically build a modular foundation of sensors, algorithms, and effectors, and eventually the required system emerges from the parts.
Building an autonomous machine forces engineers to confront a massive physical disconnect. You have unguided, heavy mechanical hardware on one side and purely abstract computational code on the other. The act of thinking is strictly a computer science function, but sensing the environment and affecting physical change, moving, lifting, steering, are problems of physics and mechanical engineering. They don't naturally speak the same language. This document is the May 1982 R&D Plan for Army Applications of AI and Robotics. It was commissioned by the U.S. Army to chart a practical path for developing autonomous combat systems. The Army needed to know how to take emerging, lab-bound artificial intelligence and integrate it into the unpredictable, chaotic environment of a real-world battlefield. Before a single prototype could be manufactured, SRI International had to invent a unifying systems architecture. They needed a framework that allowed rigid code to interface with physical chaos. The resulting report serves as a strict structural blueprint for modern autonomous systems engineering,
laying out the exact requirements for building an embodied agent. To build this system from first principles, we have to start from the ground up. The foundation of the robot is its physical body, represented by the sensing and affecting layers. These layers are constrained by physics and the limits of available hardware, like optical cameras, tactile sensors, and motors. To make that physical hardware useful to a computer, you need a translation layer. This is the interpreting module. Interpreting takes raw, noisy data from the sensors and converts it into structured, machine-readable information. The reverse process requires an equal and opposite translation layer, generating. Generating takes abstract machine logic and converts it back out into specific voltage outputs and physical motor commands. Without these two translation layers, a camera is just a piece of glass, and a motor is just a heavy magnet. They remain completely disconnected from the machine's internal logic. Sitting above those translation layers is the brain of the operation, the world model. It is the agent's internal state machine. It holds the digital representation of the physical environment it occupies. Inside that world model sits the reasoning engine, acting as the core logic processor. Reasoning continuously updates the world model based on the new, structured data flowing up from the interpreting layer. The engine then evaluates that updated model to decide what specific actions to push down to the generating layer. This flowchart from the 1982 report maps out the complete, unified model of artificial intelligence and robotics. This continuous feedback loop provides the mechanical and logical sequence required to transform unguided hardware into purposeful, autonomous action. Taking this pristine theoretical architecture and dropping it onto a real-world, unpredictable battlefield requires a system of strict, uncompromising categorization. To bypass science fiction and isolate actual engineering problems, SRI employed a rigorous 5-step methodological funnel. As outlined here under Application Concept Derivations, they analyzed potential combat scenarios through 6 specific viewpoints: threats, units, equipment, functions, environment, and personnel. This table shows how that funnel filtered 100 raw hypothetical concepts down into 10 highly defined R&D application categories, pairing each category with a specific engineering example. The unified model served as a strict sorting mechanism. It allowed the Army to classify hypothetical machines based on the ratio of cognitive processing versus physical affecting required to build them. Mapping these applications against the unified model revealed drastically different timelines for deployment. This page identifies the Mine Clearer as an application that could be developed immediately using standard 1982 technology. A mine clearer was feasible because its operation is entirely physical. It requires basic sensing and affecting, but zero complex reasoning or world model updating. Compare that to another proposed application, the light-fighting sentry, envisioned as an autonomous weapon platform. Paragraph 13 here details why the light-fighting sentry had to be deferred. The machine required complex mobility, navigation, and the ability to independently identify targets. This recommendations list quantifies exactly what was missing. SRI identified 97 specific research tasks across computational vision, language generation, and action planning that stood between current hardware and long-term autonomy. The unified model performed engineering triage, isolating the specific technological bottlenecks that stood in the way of advanced autonomy. Returning to the architecture reveals its greatest long-term engineering advantage: strict modularity. By dividing the agent's functions into discrete compartments, you isolate the components. This means hardware and software modules can be developed, tested, and integrated on entirely independent timelines. If optical technology advances, a basic sensing module can be swapped out for a newer version without having to rewrite the core reasoning module above it. Paragraph 11 highlights this explicit strategy, stating that successful future applications will require precise system integration and modularity. By decoupling the brain from the body, SRI ensured an entire system wouldn't become obsolete simply because a single sensor improved. SRI formalized this architecture decades before the physical hardware existed, establishing a permanent structural taxonomy for artificial intelligence that persists in autonomous engineering today. These 1982 divisions define the operational loop of contemporary embodied agents. Modern autonomous systems replicate this process. Raw sensor inputs are interpreted into a structured world state, processed by a reasoning core, and finally generated into physical commands. While computational power has scaled exponentially since the 1980s, the engineering logic of mapping abstract code to physical reality remains identical to the SRI model. It proves a lasting systems engineering truth. Before you can deploy intelligence, you must first design an architecture robust enough to contain it.
By the early 1980s, automating combat was a primary objective for the military. However, creating an independent fighting machine required solving a complex architectural problem. At the time, artificial intelligence and robotics were treated as separate academic disciplines. Researchers built digital brains in a vacuum, while mechanical engineers designed bodies without intelligent direction. To bridge this gap, the Army Engineer Topographic Laboratories issued a mandate to SRI International. In May 1982, SRI delivered this document, the R&D Plan for Army Applications of AI Robotics. SRI was handed a massive scope. They were asked to evaluate 100 distinct hypothetical concepts for intelligent combat systems to determine what was actually possible. But the researchers immediately hit a wall. Establishing a coherent research and development pipeline for a complex weapon system is impossible if software logic and physical hardware are evaluated in isolated silos. To accurately assess whether an autonomous weapon was feasible, defense engineers first had to invent a single framework that erased the barrier between computer science and mechanical engineering. Traditional computing of the era viewed machines as passive calculators, desktop systems waiting for inputs. A combat robot, however, has to be an active participant in a hostile environment. It must exist in a continuous feedback loop with its surroundings, taking in data and asserting physical force. SRI's solution to formalizing this loop was the unified model of artificial intelligence and robotics. SRI designed this as a philosophical architecture to measure the technical difficulty of any proposed system, regardless of its physical form. To understand why modern autonomous systems are built the way they are, we have to look at how SRI defined this loop. By mapping out the cognitive and physical steps required to execute a single task, the unified model exposes exactly where the technology of the early 80s falls apart. This diagram introduces the framework of the unified model. We start from the ground up, at the physical interaction layer. Sensing is the gathering of raw data from the environment, via visual, tactile, and range sensors. Affecting is the kinematic output, the hands, arms, and locomotion required to manipulate that environment. But raw sensor data and raw motor commands are completely useless to a computer without an intermediary layer. That requires a move up to the cognitive bridge layer, interpreting and generating. Interpreting translates incoming raw physics, like pixels from a camera, into labeled state data that a computer can understand, such as computational vision. Generating does the reverse. It translates abstract decisions into specific physical pathways and motor commands. This architecture was so central to SRI's methodology that they structured their entire technical report around it, mapping each technical chapter directly to a layer of the unified model. Without these highly complex bridge layers, an AI is essentially trapped in a jar, completely unable to understand or affect the physical world. Looking at the top of the architecture, we find where the ultimate logic resides. Reasoning is the core AI function. It assimilates the interpreted data, plans actions, and monitors the execution of those actions. Notice the final, encompassing boundary that houses this core. This is the world model. It acts as the machine's internal, constantly updating digital copy of the battlefield. The reasoning node cannot look at the real world directly. It can only make decisions based on what exists within its world model. The complete cycle flows in a single direction, sensing to interpreting, updating the world model, reasoning making a plan, generating the commands, and effecting the physical change. True independent combat autonomy demands that this entire loop cycles continuously, rapidly, and flawlessly in the real-world environment. SRI used this diagram as a diagnostic tool to evaluate the 100 proposed Army concepts. This table shows how they compressed the 100 concepts into 10 broad functional categories: This let them isolate which parts of the unified model each concept stressed the most. Take the Brigade Mission Planning Aid. This software relies almost exclusively on the reasoning and world model nodes to process logistics, requiring zero physical effectors. By contrast, the tank ammunition handler heavily stresses the generating and effecting nodes to safely move physical, heavy ordnance inside a vehicle. By running concepts through this architectural stress test, engineers could stop guessing. They could mathematically pinpoint exact technological bottlenecks. These bottlenecks were identified as technology gaps, the specific points where the 1982 state-of-the-art failed to execute the unified model. SRI generated a massive, granular list of 97 specific research tasks required to patch these gaps across the model. Highly ambitious, fully integrated concepts like a light fighting sentry or a tactical threat projection system were deemed impossible because they demanded simultaneous breakthroughs across every single node. The results of this feasibility filter were severe. Out of 100 proposed ideas, almost nothing was left standing for near-term development. Only 4 candidate applications survived for immediate development using existing 1982 technology. These 4 survived for one specific reason. None of them required the full unbroken loop of the unified model. The filter proved that a system was only viable if it deliberately avoided the complexity of crossing the software-hardware bridge. It had to remain either a purely physical tool or a purely digital database. How was the military supposed to reach full autonomy if integrated systems were decades away? The final mandate prioritized modularity as the only viable path. They needed to develop distinct hardware modules and discrete software modules separately. As technology advances, you upgrade the system by simply swapping out an obsolete software module for a smarter one, leaving the hardware intact. Within the unified model, you don't build the whole diagram at once. You build the boxes separately and standardize the interfaces between them. This 1982 framework formalized the separation of physical hardware from software logic, anticipating the modular requirements of modern autonomous systems. The SRI R&D plan showed that intelligent combat systems required the patient, modular integration of isolated components over the course of decades.
In May 1982, the U.S. Army Engineer Topographic Laboratories commissioned a study to map the future of combat automation. The report, produced by SRI International, identified 100 potential applications for artificial intelligence and robotics in Army combat and support. At the time, artificial intelligence was generally categorized as software logic, while robotics was treated strictly as mechanical engineering. This division created friction for engineers trying to build autonomous agents, who found that the software brain and the mechanical body were often designed as separate systems. SRI's approach treated cognition and physical action as a single, continuous feedback loop. By linking the software brain directly to the mechanical body, the report established a unified systems architecture. This diagram shows the unified model SRI proposed to bridge the gap between AI and robotics. The cognitive functions sit at the center of the model, interpreting, reasoning, and generating. Below them are the physical interfaces, sensing and affecting. The bridge between these two worlds is the world model, an internal digital representation of the system's outside environment. Data flow follows a specific path. Hardware pulls in data through sensing, which software then interprets to update the world model. The system then reasons about that model, generates a specific plan, and executes it through the physical affecting module. This provided a standardized theoretical language, allowing abstract combat concepts to be translated into specific hardware and software modules. The brainstorming phase produced 100 distinct concepts for autonomous combat systems. Planning R&D for 100 separate projects at once is a logistical impossibility. To manage the workload, SRI organized these concepts into 10 broad categories based on their underlying technological similarity. The resulting list ranged from human-machine interface aids to autonomous weapons and system controllers. We can see how this works by mapping an expert advisor, like an automated repair manual, onto the unified model. An expert advisor relies on reasoning and interpreting to assist a soldier, but it lacks any physical affecting components. This allowed engineers to identify exactly which parts of the architecture each military system would rely on most.
Applying this model revealed a significant reality check. Most of these categories were beyond the reach of 1982 technology. Only 4 of the 10 systems were identified as candidates for immediate development. The mine clearer was a prime example of a viable near-term system. Its feasibility came from its restricted operating environment and limited input requirements. On the unified model, it requires only rudimentary locomotion and point sensing, with almost no complex reasoning required to update its internal world model. Similarly, the tank ammunition handler was viable because it operated within the fixed, predictable physical space of a tank interior. In the 1980s, autonomous success was possible only if the physical variables of the environment were strictly constrained. The remaining SIS systems were deferred, requiring decades of research to overcome specific technological roadblocks. The Safe Return Controller was one such concept, originally designed to navigate a robotic platform back to base entirely autonomously. This required integrated monitoring and diagnostic systems to track the platform's internal health in real time. When mapped onto the architecture, a specific failure point emerges. The connection between sensing and the world model fails.
The system cannot reliably interpret chaotic status data fast enough to maintain an accurate internal reality. The river reconnaissance system faced the same bottleneck. Navigating a river requires fusing multiple unreliable streams, currents, terrain, and movement, into a cohesive plan, a process the report called information integration. This confirmed that unconstrained environmental interpretation was the ultimate roadblock, as physical robotics had outpaced cognitive software. Instead of building impossible systems, SRI designed a roadmap of fundamental research to bridge these gaps. The plan isolated 97 specific research tasks distributed across 5 fundamental areas. The areas requiring the most investment were clear from the task counts. Computational vision required 12 tasks, while action planning required 16. These 2 fields, computer vision and predictive planning, are now the primary focus of modern neural network development.
SRI also emphasized system modularity in their recommendations. They theorized that hardware and software code should be common and swappable across different military applications. Solving computational vision for a river drone meant that same software module could eventually be used in a safe return controller. The 1982 report established a distinction between individual gadgets and systems architecture. While the 1980s physical hardware looks archaic, the underlying software logic remains highly applicable to modern autonomous systems. Modern neural networks still follow the same sequence. They must sense, interpret, reason, generate, and affect against a world model. By mapping these requirements in 1982, SRI defined the core architecture of autonomy decades before the technology existed to fully implement it.
In May 1982, the U.S. Army tasked SRI International with an immense logistical challenge: building a roadmap for integrating artificial intelligence and robotics into combat support. The resulting study identified exactly 100 theoretical concepts for automated warfare, ranging from data access systems to robotic scouts. This created significant engineering tension. Planners had to structure funding for 100 disparate concepts, relying on technology that had not been invented yet. Realizing these systems in the 1980s required a pivot away from individual gadget design in favor of strict high-level systems engineering. SRI determined it was inefficient to plan 100 separate, siloed robotic projects. Their solution was to engineer a single, unified architectural model capable of supporting every concept on their list. By breaking down AI and robotics into modular cognitive and physical functions, engineers could map the exact technology gaps needed to build an automated military infrastructure. This shifted the focus from predicting specific weapons to architecting the underlying technological foundation they would all share. This paradigm unites all autonomous systems into a single schematic. Sensing and affecting blocks represent body hardware governed by physics. Above them are the cognitive brain functions: interpreting, generating, and reasoning. These operate within the world model to determine what the body should do next. By strictly separating hardware physics from software cognition, SRI created an actionable baseline to evaluate any theoretical military robot. To apply this model, SRI first had to organize the raw list of 100 concepts into a manageable structure. They clustered these ideas based on technological similarity and military use.
This distillation resulted in 10 broad functional categories, each represented by one detailed case study, such as a tank ammunition handler or a river reconnaissance system. Under this model, a logistics bot and a weapon system might be functionally identical if they shared the same underlying technological requirements. This categorization reduced 100 isolated engineering challenges into 10 parallel R&D tracks. SRI then analyzed the research needed to bring one example from each of the 10 categories to life. The report concluded that only 4 of the 10 specific examples could be started with 1982 technology: the mine clearer, the brigade mission planning aid, the tank ammunition handler, and a quick data access system. Other concepts faced much longer horizons. 2 of the 10 examples required deferring development entirely until the year 2000. Systems engineering forced planners to prioritize documented technology gaps over strategic desires. We can see this feasibility gap by contrasting the mine clearer with the light fighting sentry. The mine clearer was deemed immediately feasible because it operates in a highly structured environment, with basic, repetitive, effecting requirements. In contrast, the light fighting sentry was deferred for decades. Unstructured combat environments are much more difficult to program. In an unpredictable environment, a robot requires advanced interpreting, like computational vision, and deep reasoning to update its world model dynamically. SRI recognized that these cognitive software functions were years away from deployment-ready maturity. The timeline for an autonomous system is determined not by its physical components, but by the unpredictability of its operational environment. After mapping these gaps to the unified model, SRI advised against funding the 100 robots directly. Instead, they identified 97 specific research tasks necessary to advance the state of the art. These tasks target the cognitive and physical blocks of the unified model, with a heavy focus on the software brain, including 12 tasks for computational vision and 8 for language interpretation. This strategy targets fundamental capability gaps at the component level rather than chasing end-state products. This methodology led to a modularity blueprint for the Army. Because many of the 100 military concepts shared fundamental similarities, research into those 97 tasks would yield common modules. A single functional computational vision module could be slotted into a threat projection system, a mine clearer, and a sentry simultaneously. The 1982 SRI report provided a framework for viewing AI not as isolated gadgets, but as a systemic modular infrastructure designed to scale across the future of warfare.
In the early 1980s, computing power was measured in kilobytes, and complex data processing required massive spinning reels of magnetic tape. Despite these limitations, SRI International delivered a report in May 1982 detailing a comprehensive research and development plan for Army AI and robotics. The study was commissioned by the U.S. Army Engineer Topographic Laboratories. During the Cold War, defense agencies required long-term technological forecasting to stay ahead of evolving threats. This document targeted an ambitious goal: mapping the integration of artificial intelligence into live combat environments. The researchers presented a dense 324-page systems engineering blueprint to the military. This document codified the mathematical and logical roadmap for modern military robotics, establishing technical requirements decades before the hardware existed to implement them. At the time, engineering efforts were hindered by a strict separation between artificial intelligence and robotics. AI was seen as a domain of pure software and mathematics, while robotics was treated as a mechanical problem of motors and chassis. The SRI report moved away from this siloed approach by introducing the unified model. Their thesis stated that an intelligent robot must be able to concurrently think, sense, and affect. They used a biological analogy. Thinking is a brain function, while sensing and affecting are body functions. The authors explicitly refused to distinguish between the two fields, demanding a holistic engineering approach. True autonomy requires a closed perception, planning, control loop. This realization established the engineering standard for all subsequent defense research. We can see how a machine actually processes reality by breaking the unified model into its structural layers. The lowest tier is the external interface, the body. Sensing is governed by physics. It captures raw environmental data through cameras, radar, or tactile sensors.
Effecting is driven by mechanical engineering. It encompasses the manipulators, treads, and weapons that alter the physical world. The middle tier serves as the translation layer, bridging hardware and software. Interpreting algorithms must parse raw, chaotic sensor data into computer-readable facts. On the other side, generating algorithms translate digital intentions into the physical voltages required to move motors. At the top sits the cognitive center, the brain. The world model is the machine's internal digital map, which is constantly updated by information flowing up from the interpreting module. Reasoning is the central logic engine that formulates tactical plans based on the state of the world model, completing the loop by passing instructions down to be generated as action. This framework is a powerful diagnostic tool. Any military concept can be plotted against this architecture to locate its specific point of technical failure. SRI tested this model by analyzing 100 theoretical combat applications. To manage the complexity, engineers distilled those ideas into 10 functional categories. By passing one example from each category through the unified model, researchers could analytically predict their feasibility. Their findings showed a sharp split in timelines. Development for only 4 examples could begin within 10 years, while the rest required deferral until at least the year 2000. The early starts included applications that were theoretically possible using 1982 technology. One candidate was a tank ammunition handler, a heavy machinery system designed to move artillery rounds. The architecture reveals why this worked. It relies on affecting hardware but operates in a controlled environment, requiring almost no complex reasoning logic. The deferred concepts required fundamental research breakthroughs that stretched beyond the year 2000. The light fighting sentry was the primary example of a deferred application. A robotic sentry faced immediate bottlenecks in the unified model, requiring impossible leaps in interpreting to identify targets and reasoning to execute autonomous tactics. The timeline for autonomous weapons was gated by a quantifiable deficit in computational perception and logic. Physical robotic strength was not the limiting factor. The SRI engineers proved these multi-decade delays through granular breakdowns of each proposed system. We can track how they dissected a complex concept like the tactical threat projection system into distinct design components. They identified specific prerequisites, from database structures to interface designs, that had to be solved before the system was viable. The actionable output of this analysis was a matrix of 97 research topics required to achieve autonomy. The gaps were heavily weighted towards software logic, with 12 tasks identified in computational vision alone and 16 dedicated purely to action planning. Solving just one of these vision tasks in a military environment required a level of mathematical complexity that was staggering for the era. Defense strategy requires stripping the science fiction out of a concept and replacing it with distinct engineering problems. To manage a 40-year development cycle, the report offered a key strategic recommendation. Their final findings heavily prioritized the critical concept of system modularity. The architecture of the unified model inherently supports this modular approach, enabling the fielding of evolutionary versions. This allows for upgrading a robot with a smarter interpreting software module a decade later without replacing its physical chassis. This decoupling of software evolution from hardware lifespans provided the technical foundation for the agile development cycle seen in modern defense programs. The report delivered a final warning regarding the technology base. The technology base is the foundational science and algorithm research that must precede any physical prototype. There was a significant gap between the algorithmic ambitions of these engineers and the physical computing reality of 1982. Despite these limitations, the SRI engineers accurately mapped the trajectory of the next 40 years of military research. True autonomy is achieved by perfecting the mathematical architecture that connects the physical world, the digital brain, and the mechanical body.